Wait, good morning, everybody. In the last lecture, we were talking about constructors in your subclasses. And so the rules that are here apply to every class that you make in Java. So this includes the classes that we've made so far. You'll notice that we haven't been following those rules, but there's a reason for that. So number one, the first line in the body of a constructor must be a call to another constructor. So we haven't been doing that in any of our previous classes. So for example, if we go over to Eclipse, and you look at the counter class itself, right? On the first line of this constructor body, there is no call to another constructor, right? But the rule says there has to be one. There is an exception to the rule, right? So if you don't call a constructor on the first line of your constructor, then Java inserts a call to the superclass constructor for you, right? And so what's going on in the counter class or our point2 class or any other class you've made in the course so far is that if you don't call the superclass constructor, it gets called for you. So in other words, the compiler silently inserts a call to the superclass constructor, and it looks basically like that. Right? So the keyword super is used to call the superclass constructor. It has one other use, which we'll get to in a little bit. Right, round bracket indicates that this is a call to the constructor and not a method. And so this calls the object no argument constructor. Because remember, counter, even though we didn't say it, it actually extends big O object. Big O object. Right? And so you don't normally say that either when you make a top level class. Right? If you don't say it, then the compiler automatically inserts that as well. Right? So when you make a regular class, what's actually happening is you are extending the class java.lang.object. In all of your constructors, there's a call to the object constructor here. And I'll explain why you need to do that shortly. Okay, so if the superclass no argument constructor doesn't exist or it's private, you've got a problem. Right? If the compiler is going to silently insert that line, right, and the constructor, and that constructor is private, right? So the superclass constructor here is private in object, which it's not. But imagine that it was. That line's not legal because that constructor is not visible inside from another class. Okay, so if you're going to call a constructor of the same class. Sorry, if you're going to call another constructor from a constructor, the only place it can happen is on the first line of the constructor. Right? So not only does that line have to be there, or it's supposed to be there, the only place it can be is there. Right? There's no other way to call, you cannot call a counter constructor or an object constructor from anywhere else. There is an exception to that rule. So if you're actually going to make a separate counter object, for some reason, counter C equals new counter. Right. You are allowed to call another constructor explicitly using new. So that's legal. In this particular case, this doesn't work, right? Because this is an infinitely recursive constructor now. Right? Our counter constructor makes a new counter, it calls itself right there. Right? So that makes another counter, which calls itself right there, which makes another counter, which calls itself right there, and so on and so on and so forth. So you normally don't want to write this sort of thing. If you're in a strange position where you actually have, you actually want to make another, in this case, counter object from inside a constructor, you have to call a different constructor, right? So I could call, for example, that constructor there, and everything would be fine, right? So 0, right? So that's legal. But if you want to call another constructor to initialize this object, it has to happen on the first line. Finally, if you're creating a subclass object, if you're in the constructor for subclass object, you have to call the superclass constructor at some point. Right? And the reason you have to do this is because, back here. So back in the counter example, when you say that counter extends object, you are saying a counter is an object. In Java, that means every counter object has a big O object inside of it. How do you initialize an object in Java? You have to call a constructor, right? So the purpose of that constructor call is to initialize that part of a counter object. So I'll have more to say about that in a minute. Now, you don't have to call just the no argument constructor. You can call any superclass constructor, and that'll work just fine. All right, so let's move on to the second constructor. We want to add a second constructor that initializes our stopping counter to some non-negative value. Okay. So we want to put in a constructor that takes in a value here, right? And now you have to decide what's going to go here. Okay, so it turns out, oh, where'd it go? It turns out there's a lot of things you can put here. And this is one of the confusing parts about creating a subclass. So if you go back 2 slides and you look at the rules for creating a constructor, you might conclude that I have to call a superclass constructor here. And you would be right. Right. Sorry, I have to call a constructor here because this is the first line of a constructor. Right. So a possible solution is the following. Hopefully I have it right here. Here. Right. So in this version of stopping counter, right, I say, well, I have to call a constructor. At some point, I have to call the superclass constructor. I might as well do it right now. Right. So let me call the superclass constructor that takes in a value. Right. You go and look in counter. You look at the implementation of that constructor, right? And you see that it's ROM. The value is less than 0. Oh, you. I guess that's the correct version of it, right? And so the counter version of the constructor sets the value to the specified value after making sure it's legal. Right. And that's nice because the stopping counter, well, it also has to make sure that the value is legal. Right? By using the superclass constructor, we've already checked the value is legal, so we don't have to do it again. Right. And that's all you have to write. That's all we need to do for this particular constructor. Right. There's no other fields, so there's nothing else to do once we've initialized the value of the counter. However, there's lots of other things you can write here as well. You have to call a constructor. That doesn't mean you have to call the superclass constructor. Right? You can also do the following. Right? So I can call the no argument constructor. Oh, notice that this it detects that there's an error here. So let me fix this one. Put it back the way it should be. Okay. So I'm allowed to call one of my own constructors. So a stopping counter constructor can call another constructor using chaining. Right, so I can call that constructor. That constructor calls the superclass constructor, so that's good. That satisfies rule number 3. The superclass constructor has to be called at some point. Right, the value of our counter is now 0. Right, so now I can go ahead and set the value of our counter to this dot value, assuming this dot value is legal. Right, so let me go copy the code from counter. So if you wanted to, you could write that now, right? And that would be fine as well, right? So validate the value. If the value is legal, go ahead and set this value to value, right? Why can I write this line? Because value is protected in counter, right? Which means I have access to it in the subclass, and I can access it by name. Right. Whether you access it with this dot value, you could also write super dot value, and that would be fine as well in this case. Doesn't matter. In the subclass, you would normally write this dot value. So you could also write that. Right. What else could you write? Well, I technically don't need that call to the constructor. Right. So if I don't call the constructor on the first line, what happens? Right. Well, the superclass no argument constructor gets called. Right. So that constructor gets called for me, which is great. So I now have a value, a counter whose value is 0. Go ahead and validate the value and set this dot value to value. Right. So it turns out there's many ways to implement this constructor. The easiest way to do this, though, is with the first option. Right. So find an appropriate superclass constructor that does all of the work for you. And that happens to be the one that takes in a value. right? And that simplifies your life. That satisfies all rules, right? And is the easiest to write. It's also the easiest to read and understand. Right? Anybody who's used to doing this sort of thing can look at this line of code and say, oh yeah, so I'm initializing the superclass part of the counter to value, and that's all you need to do. Yes.
How does it know which superclass to use?
It's always the direct. It's always the direct superclass. So there's no way for you to go to a non-direct superclass. There's no way to access, say, if there was another class above count. So there's no way for me to access an object constructor, yeah, from this particular class. Yeah. Right. So lots of things could go here. So the slides goes on to use the chaining technique. Right. So here, oh, sorry, I lied, doesn't it? Oh, here. So the first one, it changes the first call to use constructor chaining. Right. When you chain to the second constructor, right, that calls the superclass constructor that takes in a value. All right, so why on earth do these rules exist? They seem overly complicated, right? First time you're using inheritance, if you see these rules, it's like, why on earth am I doing this? Right? Inheritance must be a mess. It kind of is, to be frank. The reason you have to do all of this is because of how subclasses actually work in many object-oriented programming languages. All right, so what is a subclass exactly? So it kind of looks like a new, well, it is a new class, right? So when you subclass something, you are making a new class. It has all of the same public features. So when I say API, that just means the public features of the of a class, right? So it has all of the public features of the superclass, right? With perhaps some additional methods and fields, right? So it looks like a new class. You've added some extra stuff to it, right? Now, does that mean that a subclass is just a copy of the superclass, right? With extra stuff glued into it? The answer is no. That's not what happens. Right. So what actually happens is that your subclass has a field, right, that is an object of the parent class. Right. So inside every stopping counter is a counter object, right? And you can think of it as being a field of stopping counter, right? So when you have a field in a class, you have to initialize that field, right? How do you initialize the field? You have to call the constructor for the field, right? What is the type of the field? It's a superclass type. That's what you have to call the superclass object class constructor from inside of every subclass constructor. Now, why does it have to be on the first line? And so that's the big question, right? So why can't I call the superclass constructor from somewhere else, right? Maybe on the last line of the constructor. Right. So why is a constructor call needed? Because a stopping counter is a counter, so it has a counter subobject, right? That counter subobject has to be constructed. So what's going on in Java is the following. So this is just a picture of what's happening. It's not, it doesn't correspond to a memory diagram or anything like that. Right? So this is just a conceptual picture. So I have a stopping counter, and I'm gonna, oops, wait, that's new stopping counter. And sure, let's do it that way. Okay, so I'm going to call the stopping counter constructor. So what happens? Well, I'm going to call new, right? And then I'm going to make a stopping counter with new. So when you call new, you get the stopping counter object, right? So it shows up somewhere. All right, so now the constructor starts to run, right? The constructor wants to fill in the fields of the stopping counter. Okay, so the very first thing is a call to the superclass constructor, right? So that's the rule in Java. Right. Why? Because you have to initialize the counter part of stopping counter. So the stopping counter constructor starts to run, right? It makes a new counter object, right? So it calls the superclass constructor, which makes a new counter object. And now the counter constructor starts to run. Right. So what does a counter constructor do? Well, remember, counter is a subclass of object. So it makes the object part of the counter. Right. So notice that a stopping counter also has an object inside of it, right? Via its counter object. So the object constructor now starts to run. Right. I don't know what it does. It does some stuff. I haven't looked at the source code for it. right? Whatever it does, though, it initializes whatever fields happens to be in the big O object part of the counter. So it eventually finishes, right? So that object is now fully constructed and initialized. And that means the counter object can continue running, right? So the counter the counter constructor can finish running, right? What does the counter constructor do? Well, it sets the value, right, to 1 in this case, right? So whatever field belonging to counter now gets set to 1, right? So the value, the field called value, gets set to 1. And so now counterpart of the object is finished being created, right? So now what can happen? Well, finally, the stopping counter constructor can finish running, right? So there's nothing left to do, right? The value of the counter has been initialized. Stopping counter doesn't have any additional fields. So finally, at this point, our stopping counter object is now fully created. And so notice that the order in which all of the objects are finished being created is from the inside out, right? The first object that gets finished, completely initialized, is the object part of the counter, right? The second part, or the second object that gets fully initialized, is the counterpart of the stopping counter, right? Oops, sorry. And finally, the last object that gets fully initialized is the stopping counter object itself, right? The reason why the constructor call happens on the first line of every constructor, right, is to make sure that all of the sub-objects get constructed first before you actually attempt to construct the to initialize the object that you want to initialize, right? So in other words, if you don't initialize all of the subparts of stopping counter, it's possible that whatever stopping counter is trying to do will run into an error of some kind, right? Because the stopping counter constructor might want to do something with that field value. It might need to access it to look at its value, or it might need to change it or something else, right? So if, for example, if stopping counter was allowed to run some code before calling the counter constructor, right? So imagine that you could set the value to 1 before the counter constructor runs, right? And then you call the counter constructor, perhaps incorrectly, you don't pass in any value, right? The counter constructor is going to come along and change that value back to 0. And now you have an incorrectly initialized object. So the language specifically says when you create a subclass, its sub-objects are created first before you can do anything else inside of the constructor. And so that's why rules 1 to 3 are needed, right? You have to initialize the sub-objects on the first line first, so the constructor call must happen on the first line. The constructor call has to be there because there's sub-objects that need to be initialized, and the way you initialize something in Java is with a constructor. All right, so that explains why those rules exist, hopefully. So finally, we can now finish off our stopping counter class. Right, so remember, the whole purpose of all this was to create a counter that stops counting when you hit integer max value. So finally, we can override events. Right, it's easy to do. Right, so in stopping counter, you just check, is the current value not integer max value? Right, if it's not integer max value, I can add 1 to it. Right, so add 1 to the value and away you go. If it is integer max value, I can't add 1 to it safely because it'll overflow and wrap around to the integer min value, right? So do nothing, right? And that's it. So it's pretty easy to implement advance in this case, right? And so there's an example of overriding a method that was inherited from its superclass, right? The counter version of advance, remember, looks like that. Right, so it wraps around to 0 when it hits integer max value. I want to change that behavior, so I simply replace the definition of advance by overriding it, and make sure that when you get to the maximum value, it stops counting. Okay, so the stopping counter class is not hard to implement, right? So let's go back and just quickly look at its full implementation. Right, so we have some constructors in it. I guess the thing I didn't mention is that a subclass does not inherit its superclass's constructors. So the constructors are not technically what are called members of a Java class. Because they're not technically members, they don't get inherited. Which is another reason why you have to explicitly call them yourself. Okay. So here's one constructor. There's a second constructor. There's no copy constructor here. But if you wanted to put one in, and you probably should, because the counter class has one, it's easy to implement. Okay. You can also do something a little bit different here. Okay, so I want to make a copy constructor. Now the question is for the copy constructor, basically I want to copy the value from another counter, right? And so the question is what goes in here, right? So all of our copy constructors so far would look like this. That, right? And you would write something like, well, counter has a copy constructor, so I can do this. Right, so in the counter class, there is a copy constructor there, right? It takes in a counter object, right? So I can technically write that, right? And you might say, oh, no, you can't write that, right? Other is actually a stopping counter, but counter requires just a plain old big C counter, right? But this is fine, right? Why is this fine? Because stopping counter is a subtype or a subclass of counter, right? And that means every stopping counter object is substitutable for every counter for a counter object. So if I need a counter object, I can safely pass in a stopping counter object other. Right? So this call is in fact legal, and this is the easiest way to implement this constructor. Right? And so this lets me copy another stopping counter object. Okay. But there's no reason I can for me to only be able to copy another stopping counter object, right? If I just want to copy the value from the other counter, then well, I can take in any counter object, right? So I can write that instead. Can I still copy another stopping counter object with this constructor? The answer is yes, right? So if somebody passes this constructor a stopping counter object, that's fine. A stopping counter is a counter, right? It's substitutable for counter. So this copy constructor will also accept another stopping counter, right? And so that is an example of a copy constructor, right? The type here doesn't exactly match the type here, right? So at first glance, it doesn't look like a copy constructor, but that type there is a super type, right? It's the superclass of stopping counter. And so this is in fact a form of a copy constructor. And so if you wanted to put the copy constructor in, that's the easiest way to do it. Yes.
A constructor of a subclass that has fields the superclass doesn't have.
Yeah.
And you need to copy them.
Now you have to do that stuff here, right? So if there are extra fields in stopping counter, you have to set them here. Okay, so what else? Oh, and then there's advance, right? So the mechanics of inheritance are straightforward if you remember the rules for the constructors, right? Extend the class that you want to extend, right? Remember all of the rules for your constructors, right? There must be a call to the superclass constructor on, there has to be a call to a constructor on the first line. You have to call the superclass constructor at some point. The only place you can call another constructor is from the first line, right? And then override whatever methods you need to override. It could be the case that you don't have to override any methods. So all that ends up in your subclass are a bunch of constructors, right? Because the superclass methods do everything that you need, right? So you don't have to override methods in the subclass, right? Oh, and then finally, if you want, add extra methods here. Right. So if there's some methods in that you want to add to the stopping counter that don't exist in counter, you can add them here. All right. So one more example using counter. We've got a counter now that wraps around at integer max value. We've got a counter that stops. The other thing that you might consider doing is throwing an exception. Right. So you might want to throw an exception to indicate that you can't count any further. And it turns out this is not a particularly good idea. And if I remember, we'll come back to this when we talk about how post conditions on methods interact with inheritance. Right. But we can do this for the time being, and everything will be okay for now. So I want to create a class called throwing counter. It throws an exception when we hit integer max value. Right. Again, there's no fields, right? I don't need any extra information except for the value of the counter. Right. What do my constructors look like? Well, they look exactly the same as the stopping counter constructors. Right. That calls the superclass constructor passing in 0, so sets the value of the counter to 0. Right. That calls the superclass constructor that sets the value to value. Right. Now advance. So what does advance do? So when it hits maximum value, it throws a runtime exception. You could throw something else. I just picked runtime here for simplicity. Right. How do you implement it? Well, you just override advance. Right. You check, is the value not integer max value? Right. If it's not, go ahead and add 1. Otherwise, throw an exception. Right. And that's it. Right. So often it's very easy to create a subclass if you're extending it in a relatively simple way. All right, so do you have to implement the counters this way? The answer is no, right? There are lots of alternative ways to create different types of counters that behave in a different way when they hit the maximum value, right? We've already seen one of those ways, right? You could use interfaces instead. So you could take the counter class right? And instead of having a counter, you can turn it into an interface, right? So public interface counter, right? You have your methods. So all it has is advance, value, and advance, right? And now you go ahead and create your classes. You create your regular counter, your stopping count, or your wraparound counter, your stopping counter, and your throwing counter classes separately, right? They all have their own separate fields and methods. Fields, methods, and constructors. Sorry, fields, methods, and constructors. Right. So if you use an interface, you don't get any of the advantages of being able to reuse a field and possibly being able to reuse methods. Right. You have to implement them all yourself separately. But there's another way to do this, also using inheritance. Right. So in the counters, right, they all behave the same except when you get to the maximum value. Right. So when we used inheritance the way we did, right, we ended up making separate classes that just override the advanced method. Right. So there is an alternative way to do this. Right. So the alternative way to do this is to make one counter class, right? And then you have a field that is an object that knows what to do when you hit the maximum value, right? So instead of creating separate counter classes, you create separate classes that decide what happens when you hit integer max value. Right? So in your advance method, you've got some object that knows what to do or how to advance or what to do when you hit max value. Right? So now you ask the object to run whatever method it has that determines what happens when you hit max value. Right? And so for that object, you could use inheritance to create that hierarchy of objects, or you could use an interface to create those objects as well. Right. So there's lots of ways to handle this problem. Right. We've done it using plain old inheritance because it's probably the simplest example of inheritance that's actually useful. But there are many ways. There are many other ways to handle this particular problem. All right. So we've talked about the basic fundamental mechanics of inheritance. Any questions so far? All right. So things do unfortunately get a little bit more complicated in inheritance. And it's because of the relationship that you are trying to model. I think there's some repeated slides here, so I'm just going to skip past them quickly. Oh, equals. Yeah, here we go. Okay. So now we come back to equals, right? So remember I told you there's two different ways of implementing equals, right? One uses get class, one uses instance of. So now we're in an inheritance hierarchy of counters, right? So the question is can I compare counters for equality, right? And if I can, what does it mean to do so, right? So is it possible to compare different kinds of counters for equality? So for example, I can compare a counter to a counter, right? I just look at its value. It makes sense that you can compare a stopping counter to a stopping counter. You just look at its value, right? The question is are you going to be able to compare a counter to a stopping counter, right? And the answer is well, it depends, right? It depends on how you want to implement this hierarchy of classes. It kind of makes sense that you should be able to compare one counter to any other kind of counter, right? Because all you care about is what is the value of the counter. If that's what you want to do, you can't use get class, right? So imagine that in counter, you have a method called equals, right? You've overridden equals from object. You use get class right there, right? So what do? We look at our current class, which is big C counter. You compare it to the incoming objects class, right? And you decide, and you look, and you ask, are they exactly the same, right? If the answer is no, you return false, right? So I have a counter, I have a counter, right? I write C1 equals C2, right? What is the result? Well, it's true, right? That counter's value is 0, that counter's value is 0. C1, it refers to a counter. C2 refers to a counter. So the equals ends up looking at the value. It sees that they're both 0, so it returns true. Here I've got a stopping counter and a stopping counter, right? So C3 equals C4, well, that also returns true, right? Now, why does it return true? We haven't put equals in stopping counter yet, right? Because stopping counter inherits this version of equals, right? Inside this version of equals, right, it checks the types of the two classes, right? So here, it looks at the type of C3, that's stopping counter, and it looks at the type of C4, that's stopping counter. So they're both the same. So we now get to this line here, right? This line here casts OBJ to big C counter, right? Now remember, OBJ in this case is a stopping counter. So this cast still works, right? Why does this cast work? Because OBJ is a stopping counter, right? A stopping counter is a big C counter, right? And so that cast is legal. Finally, on the last line, you look at the value of the two counters. Right? They're both 0 in this case, so that returns true. So this works just fine. Here's where you run into a problem, right? So if I have a counter in C1 and I have a stopping counter in C2, when I write C1 equals C2, right, what is the type of C2? Right? Well, over here it says it's counter, right? But on the right-hand side, it says it's really a stopping counter. So when you get to this line here, right, the actual type of OBJ is a stopping counter, right? The actual type of this is just a plain old counter. So these aren't the same, so now you return false. Okay. Similarly here, I've got a stopping counter and a throwing counter, right? When I write C3 equals C4, right, that calls equals for C3, right? So that calls equals for the stopping counter class. There is no equals in stopping counter, so we end up with the inherited version from counter, right? That version looks at the two types of C3 and C4. They're going to be different in this case, right? And again, these two counters won't be equal, even though their values are 0. So if you're happy with this situation, that's it, you're done, you don't care, right? If you're not happy with the situation, you have to do something else, right? So if you say, hey, look, I just want to compare the values of these two things. And so that means you cannot use get class back in counter, right? So if you're trying to do equals with mixed type comparisons, right, then in some inheritance hierarchies, comparing objects of different types for equality is sensible, right? In such cases, you must use the instance of version of equals in the superclass, right? So back in counter, right? I can't use get class. I have to use instance of, right? Remember what instance of does, right? It looks at the type of OBJ and asks, is it the type of OBJ big C counter? Right? If it is, then that's true. Right? If it's not big C counter, it asks, well, is OBJ a subclass or a subtype of counter? Right? In this case, the answer is yes. Right? And so that's also true. Right? So instance of also tests for tests if OBJ is from a class that has counter as an ancestor. And so now, if you implement it that way, the original tests work, right? So if I have a counter compared to a counter, they compare as equals, right? If I have a stopping counter compared to a stopping counter, they still compare as equals. Right? And if I have different types of counters, they will now compare as equal. Right? And so now you've got your mixed type comparisons working. Do I tell you what you can't do? All right. So there's a slide there's something that's not shown to you here. There's something that you can't do in all of these cases. Right. Did I override equals? Let's see. So back in counter, I don't think it's overridden yet. Oh, it is. Here it is. Right. So counter has the instance of comparison. Right. So what you have to be careful about is that if you are in an inheritance hierarchy, right, and you decide to override equals, right, you have to stop overriding equals at the superclass. Right. So I decide I want to be able to compare all kinds of counters, right? I can put in equals in the counter class, but I can't override it in the subclasses. At least not in most cases. Okay. So I guess the question is why can't I do that? Okay. So here, I want to write something like, so let's try to do it this way first. All right, so if you try to write that, immediately you run into problems, right? Anybody see why you run into problems? Right, so yeah. That's right, right? So we checked if it's an instance of a counter, right? And so if you pass in, if OBJ is a big C counter, that's fine, right? We get past this if statement. Now, you can't cast a stopping counter, a counter to a stopping counter, right? So remember, inheritance is a one-way relationship. Stopping counter is a counter, but the opposite's not true, right? A counter is not a stopping counter. So now this cast fails, right? And this breaks the equals contract, right? So remember, equals says that it doesn't matter which order you compare two objects in, right? A equals B is the same as B equals C, right? So if you compare a counter to a stopping counter, right? So counter equals stopping counter, right? The version of equals that you get comes from the counter class, right? So if the two counters are equal, you get true. But if you flip the order around, so stopping counter equals counter, right? The type of object that was used to call equals is a stopping counter. So now you get the stopping counter version of equals, right? The stopping counter version of equals tries to cast the counter to OBJ and you get an exception, right? So you've busted the equals contract twice, right? Equals now throws an exception, right? And x equals y is not equal to y equals x. Well, that's no good, right? So you might say, well, what happens if I change this to stopping counter? Right? That fixes the problem, surely. Yes. The answer is no, it doesn't, right? Again, if you write counter equals stopping counter, right? You get the counter version of equals. If the values are the same, you get true. Now, if you write stopping counter equals counter, you get the stopping counter version of equals, right? And now you get false because the counter is not a stopping counter, right? And so now x equals y is not equal to y equals x, and equals is busted, right? And now you run into a problem where it's extraordinarily difficult to figure out what's gone wrong in your program, right? So you might write some program or you can write your stopping counter code in your counter code, hand it out to the rest of the world, and then all of a sudden you start to get all these funny bug reports saying that when I compare two counters, they're not comparing as equals. Right? And now it becomes very hard to find where did this error actually come from. Right? So that doesn't work either. Right? So you might say, well, look, why don't I just cast it to a counter? Right? And so if I'm going to cast that to a counter, so why don't I check if it's a counter? So if I'm going to check if that's a counter, the cast here has to be also counter. Right? And you say, fine, that works now, but that's exactly the same as what you wrote back here. Right? So your override isn't doing anything. Right? There's nothing, the override is exactly the same as the original method. So you haven't done anything useful. Right? So if you're going to, if you want equals in an inheritance hierarchy, right? The first class where you want to be able to say that things are equal, you put in equals and then you have to stop. Right? There's no consistently reliable way to, again, override equals in the subclasses and have things work out the way you want it to. All right, so some of these examples back here are a little bit funny, right? So back here, I've got, on the right-hand side, I've got counter and stopping counter. But on the left-hand side, I just have counter, right? All of this code will actually, oh, sorry, question, yes. Oh, you want to fail here. So if it's not an instance of counter,
Like not an instance of stopping counter.
Yeah.
Calls
so now you want to try to do, so now you want to return super equals.
Yeah.
That fixes, I have to be careful about this. Does that actually fix the problem in this class? So yes, the answer is yes, that fixes the problem here, but it doesn't fix the problem in general. So if you wanted to write that, the way you would write that is you would return super dot equals obj. So the super keyword is used to call the immediate superclass version of the method instead. I'm pretty sure that fixes the problem here. But in general, that doesn't work. Yeah. Okay, so back here. The types on the left-hand side are all counter. Oh, wait, not here. Here, the types on the left-hand side are all counter, right? I can store a counter reference in C1. I can store a stopping counter reference in C2, right? And the reason I can do that is because a stopping counter is a counter, right? So it's substitutable for. And the same thing happens here, right? I can store a stopping counter in C3. I can store a throwing counter reference in C4. That's all fine, right? And so that leads to the question of, well, exactly what can I store in a variable? Okay. And so to answer that, you need to know how many types does an object actually have in Java, right? So with the exception of object, big O object, every object in Java has more than one type, right? So what types does an object have, right? So whatever class it's defined in, it has that type. So a stopping counter is a stopping counter. It also has all of the types of its ancestor classes. So a stopping counter is also a counter, and it's also a big O object. If your class or one of the ancestor classes implements an interface, it has all of those types as well, right? So counter implements comparable. So a stopping counter is also a comparable object. So point two, extends object, implements comparable. What are the types of point two? It's point two, right? It's all of its ancestor classes. So in that case, it's just object. It's all of the interfaces implemented by the class and its ancestor classes. So in this case, it's comparable. Right? So every 0.2 object actually has 3 different types. Stopping counter extends counter, and it implements comparable counter. So stopping counter has 4 types, right? It has stopping counter, right? It has counter. It has the class that counter extends, which is object, right? And it has comparable counter as well. Right? There's the string class, right? String extends object implements 3 interfaces. So a string is a string, it's an object, it's a serializable object, it's a comparable object, and it's a car sequence object. Right? So so objects in Java have can have many types. Oops, sorry. Right. And so that's what's meant by this term polymorphism, which is another one of the hallmarks of object-oriented programming. So if you look up polymorphism in the dictionary, it says, the Oxford Dictionary says it's the condition of occurring in several different forms, right? Java has what's called subtype polymorphism, right? So a type, a reference type, has many different forms, right? So subtypes are substitutable for their ancestor types, right? And that's made possible because the type of an object includes all of the types of its ancestor classes and whatever interfaces are implemented, right? And so that means a string, right, can be a string, it can be an object, it can be a serializable, it can be a comparable, it can be a car sequence, right? So string has many different types. Okay, so there's 2 different types. There's 2 general kinds of types that you are concerned about in an object-oriented programming language. There is the declared type, right? So when you make a variable, that's the type that you say the variable has. So when I write counter C, I'm saying the declared type of C is counter. Right? What can I do with C? Right? So I can store the value null in C if I want to. Right? Remember, null means no object. If I have a counter reference, I can store a reference. I can store that reference in C, right? So I can store a reference to a counter object, and I can store a reference to an object having a type that is a descendant of counter, right? So if I have a stopping counter object, I can store a reference to that in C. Right? What does the declared type actually do? Right? So the declared type determines what operations you can perform with that variable. So if I write if I say that obj is a big O object, I can store any object in that variable, right? So for example, I can store an array list in that variable, right? Using obj, what methods can I use? Well, I can call toString, right? Because obj says that there's a toString, because object says that there is a toString method, right? Now, when you look at this code, you say, hey, obj is an array list, right? So array list has an add method, right? But if you try to write obj.add, the compiler will say that's not allowed, right? The error that you'll get is to say that add is not a method, big O object, right? And that's because the compiler is using the type of the declared type of obj to determine what is legal to do with obj, right? Add's not a method in the declared type, therefore it won't let you call that method, right? Even though the object that's actually stored there is an array list. Right. Similarly here, T is a set, right? But it's actually a tree set. Right? All sets have an add method. So if I write t.add, that works just fine. Right? Tree set is a sortable set. So it has a first method, right? Which returns the first object in the set because everything's sorted. Right? But set does not have a first method. So this isn't allowed, even though the object stored in T is a tree set. Right? So the declared type determines what can you do with the variable, And I'm out of time. So in the next lecture, I'll tell you what the runtime or actual type actually does. So if I do this,